Hello friends, myself Professor Rajendra Baburao Gharse, Head of Electrical Engineering Department at NB Navle, Sinhagad College of Engineering, Solapur. I am having a teaching experience of 9 years. I have completed BE Electrical from Government College of Engineering Karad and MTech from Indian Institute of Science Bangalore. I have qualified GATE examination 6 times, and in the achievements I have secured the All India 7th rank with a 99.96 percentile. In my last video, we have discussed about single phase full bridge inverter Fourier series analysis with RL load, right? Today we are going to discuss the voltage control techniques in the inverter, right? Why the voltage control is required and how the voltage, that is output voltage of the inverter, can be controlled. That we are going to discuss today. Different methods. Okay, so voltage control in inverters, right? So first is why the voltage control is essential, right? So inverter, definitely inverter is a circuitry which converts DC to AC. Okay, so output is AC. Suppose at a particular application we are using a AC load, and if for the particular application the load demands the various voltage levels, right, for a operation purpose, right? So in that case we need to, or our inverter should be having a potential to vary the output voltage, right? So that's why the voltage control is required. Or as we know, in the induction motor we are having the most popular method of speed control, that is a V by F ratio constant, that is a voltage to frequency ratio constant, right? So while using the voltage to frequency ratio control, here we need to change the voltage as well as frequency, right, for controlling the speed of the induction motor. Okay, so in this case also we need to for different available voltages, output voltages of the inverter, right? So that's why the voltage control is essential. Okay, next, the voltage control methods, right? We're having the different voltage control methods. One is the external control, second one is the internal control, right? In the external control, right, we're having the again two types: externally controlling the AC output voltage and externally controlling the DC input voltage, right? As long as the technical part is considered, right, these two external control methods are having only the block diagram type of theory, the theory part, right? But the internal control is very important, right? Internal control means the control is inside the inverter circuitry itself, right? External control means we are simply adding the external blocks or the external devices. Okay, so let us discuss what is the external control of the AC output voltage of the inverter, right? So AC output voltage of inverter can be controlled externally by following methods. Okay, one is the AC voltage control or the inverter control. Okay, now let us discuss what is the AC voltage control. Okay, so here we are having the inverter, we are interested in controlling the output voltage of the inverter, right? So here, as this is the external control method, okay, ultimately what is our aim? Our aim is to vary the input voltage to the load, So here we are keeping the inverter output constant, right? Inverter output constant, but we are using the additional circuitry, that is the AC voltage controller here. AC voltage controller is the circuitry which converts fixed AC to the variable AC, that is a fixed AC to the controlled AC, right? So whatever the output of the inverter, that is the AC, that we are going to give as an input to the AC voltage controller, right? And this AC voltage controller gives the controlled AC voltage, and this voltage given to the load as an input. Are you getting the point? Means here in the external control method of AC voltage control, we are using the AC voltage controller block additional, right? We are not making changes into the, we are not doing changes into the inverter circuitry, right? But we have added the external block here, right? So this is the simplest method, right, of the external control at the AC side, right? Next, externally controlling the DC input voltage, right? Now As we know, for inverter the input is DC. Okay, now suppose for the inverter, if the input voltage is changed, whether the output voltage will change? Definitely, right? If instead of EDC, if we give it as a 4 EDC, definitely the output voltage magnitude will change to the 4 EDC. Are you getting the point, right? So similarly here, again, this is not the unique method. We can add different blocks also, right? So we are having the AC voltage here available, right? We have given it to the fully controlled, it is given to the filter, right? So fully controlled rectifier converts the AC voltage to the output DC, but that is a pulsating DC, right? So in order to control the pulsating DC to the flat DC, right, we need to use the filters, right? So after that, the output of the filter circuitry, then it is given to the inverter, right? Given to the inverter. As here we are using the fully controlled rectifier. Definitely by changing the firing angle of the rectifier, can we change the output of the rectifier? Yes, if the output of the rectifier is changing, right, that is a DC is changing, then what about the output input to the inverter? It will be changing, right? So inverter input is changed, so that's why the inverter output will change. Yes, again here we are not doing any change inside the circuitry of the inverter, right? The only change is we are changing the input voltage to the inverter. And in the previous method we have discussed, yes, we were changing the output voltage of the inverter, right? Not exactly output voltage, but we have connected the external block at the output side. Here we have connected the external block at the input side, right? These two are the simple methods, that is the external control. Next is very important, that is the internal control method, right? What is the purpose? Yes, it is used for controlling the output voltage of the inverter, right? So internal control, right? So using the pulse width modulation technique, that is the PWM techniques, most popular methods, pulse width modulation. Okay, so in the PWM technique we are having the three types. One is a single pulse modulation, multiple pulse modulation, and the sinusoidal pulse modulation, or single pulse width modulation, multiple pulse width modulation, and sinusoidal pulse width modulation, right? Now today we are going to discuss one by one in detail. Okay, so let us first discuss the single pulse modulation technique. Single pulse modulation. Here we are having the generalized block diagram of pulse width modulation technique, right? PWM technique, generalized block diagram, right? So here we are using the two blocks. One is a comparator, second one is a trigger pulse generator. Trigger pulse generator is given, output of the trigger pulse generator is nothing but the triggering pulses to the SCRs, or triggering pulses to the BJT or the switches, right? Where these switches are present, these switches, yes, are present in inverter circuitry. If we are having the half bridge inverter, yes, we are having two switches, right? And if we are using the full bridge inverter, in the output we are having, in the circuitry we are having the 4 switches, right? So simply here we are having the comparator block and the trigger pulse generator block. Be careful, the input to the comparator block is a carrier wave and reference wave, right? For the single pulse modulation technique, we are using a triangular wave as a carrier wave, and the reference wave is a square wave. Reference wave is a square wave. What is the purpose of the comparator? The comparator will compare the magnitudes of these two waves, and depending on the comparison, it gives the signal to the trigger pulse generator, right? And the trigger pulse generator will generate the triggering pulses. Triggering pulses means pulses generated to turn on the respective SCR or the respective switch which is present in the inverter circuitry, right? So now let us discuss, yes, suppose single pulse modulation technique. Okay, so we are having, yes, here reference wave is a square wave, right? Reference wave is a square wave, and carrier wave is a triangular wave. Carrier wave is a triangular wave. This VC is nothing but the voltage of the carrier wave. VR is nothing but the voltage of the reference wave, right? Now here these two waveforms are the input to the comparator circuitry or the comparator block, right? So comparator will compare, yes, the magnitudes of the VC and VR. VC is the carrier wave voltage, VR is the reference wave voltage, right? So if VR is less than VC, that is during this period, right? If VR is less than VC, sorry, if VC is less than VR, if VC is less than VR, then the comparator will develop the signal logic low, and due to that the trigger pulse generator will not generate any triggering pulses, right? So when VC less than VR, triggering pulses will not be generated, right? After this instant, right, means when VC becomes greater than VR, when VC becomes greater than VR means during this period, right, when VC becomes greater than VR, right? At that time the trigger pulses are generated and the switches which are present in the inverter circuitry will be turned on, or for example, suppose if we are using the single phase full bridge inverter, we are having the 4 switches, right, S1, S2, S3, S4. So when VC is greater than VR, switches S1 and S2 are turned on in the single phase full bridge inverter circuitry, right? Single phase full bridge inverter circuitry. So when VC becomes greater than VR, then S1, S2 are turned on, right? So when S1, S2 turns on, suppose the load is purely resistive, when S1, S2 are turned on, in the output we will be getting EDC, right? So here if you check after this instant, yes, we are having in the output voltage, that is a VL, or you can consider it as a V0 also, right? So VL is equal to EDC, VL is equal to EDC. And when VC is less than VR, when VC is less than VR, trigger pulses are not generated, means your switches S1, S2, S3, S4 all will be in the off state, so that's why output voltage will be 0. So when VC is less than VR, output voltage is 0. When VC greater than VR, output voltage is non-zero, that is the EDC, right? So switches S1, S2 will be turned on at this instant, and this will be continue into the on state till VC is greater than VR. So if you check during this interval, yes, VC is greater than VR, right? VC is greater than VR. When VC greater than VR, again S1, S2 are turned on, right? So that's why the output voltage will be EDC. So here if you check from this instant to this instant, yes, in the output we are having output voltage is EDC, right? After this instant, yes, VC becomes less than VR. If VC less than VR, trigger pulses are not generated, right? So S1, S2 are turned off, S1, S2 turns off, then output voltage will be again 0, Are you getting the point, right? Next, similarly, if you check after this instant, right, again magnitude of VC becomes greater than VR. So switches, because here we are having the positive cycle, similarly we need to generate the negative cycle, right? So when VC becomes greater than VR, again we are going to turn on the switch S3, S4 now, right? So when S3, S4 are turned on, in the output we will be getting minus EDC, right? This will continue till this instant, right? Next, so during this interval from here to here, VC is greater than VR, right? So that's why the output voltage will be minus EDC, right? And after this instant, again VC becomes less than VR, so that's why the output voltage will be 0, right? So simply can we say that when VC becomes greater than VR, output voltage will be, when S1, S2 are in the on state, output voltage will be plus EDC. When VC is less than VR, output voltage will be 0. When VC is greater than VR, in order to get the negative cycle, yes, S3, S4 are turned on, output voltage will be minus EDC. Are you getting the point, right? Now one more thing, so this is the omega t is equal to 0, right? So this is omega t is equal to pi, that is the center point of the full waveform, right? Next, and this is the omega t is equal to 2 pi, right? Similarly after 2 pi also, it is 0 here, again it is a non-zero, again 0, right? And again it will be a non-zero like this. Are you getting the point, right? So this type of waveform is known as a Cauchy square wave, okay? This type of waveform is a Cauchy square wave. Whatever we have discussed till or so far, yes, that is the output voltage of the half bridge inverter and the output voltage of the full bridge inverter, those were the square waves, right? I have drawn those waveforms here, right? So here it is a output voltage with a modulation, right? And this is the output voltage or the square wave output that is without modulation. This is the output voltage of single phase full bridge inverter. This is a square wave, yes or no? This is a square wave. It is also known as 180 degree square wave mode, right? 180 degree. Why 180 degree? 0 to pi it is a positive, pi to 2 pi it is a negative, right? So it is a 180 degree pulse we are having, so that's why it is a 180 degree square wave mode. And this is a quasi square wave. Be careful, what is the difference between the two? In the quasi square wave we are having the zero period, again non-zero period, again zero period, and again non-zero period, right? So that's why it is a quasi square wave. Are you getting the point, right? Quasi square wave and a square wave, right? Next, so this is omega t is equal to 0, omega t is equal to pi, omega t is equal to 2 pi, right? Same, omega t is equal to 0, pi and 2 pi. Okay, next, so if this is omega t is equal to pi, can we say that the midpoint of this 0 to pi is a pi by 2, right? And again, suppose the pulse width is delta, right? Pulse width is delta, right? So if this is pi by 2, so here it is a pi by 2, and if this is delta, so can we say that the half portion of this pulse is delta by 2, this portion is delta by 2, and remaining this portion is also delta by 2. So can we indicate this with pi by 2 minus delta by 2, and indicate this point with pi by 2 plus delta by 2. Are you getting the point? So this point is pi by 2 minus delta by 2, this point is pi by 2 plus delta by 2, this point is pi by 2 plus delta by 2. Are you getting the point, right? So pi by 2 minus delta by 2, and again pi by 2 plus delta by 2, right? Now next, what is the V0 RMS in this case? For the without modulated waveform, what is the V0 RMS? Yes, V0 RMS is EDC. We have already derived it, right? And also we have already derived the Fourier series analysis of this waveform, right? Fourier series analysis of this waveform, right? So we are having the Fourier series analysis. VL is equal to, yes, A0, that is the average value is a 0, right? AN is 0 because the waveform is or the signal is odd signal. And next BN, right? BN consists of, for the N is equal to 246, BN is equal to 0, and N is equal to 1357 up to the infinity. It is a 4 EDC by N pi. We have already derived, or we have already discussed it during the operation of single phase full bridge inverter, right? Now we are going to discuss the V0 RMS expression for the modulated waveform, for the modulated waveform, right? For this waveform V0 RMS, and from this, or from the expression of V0 RMS, we are going to discuss, or we are going to conclude how the pulse width delta, change in the pulse width delta changes or causes the change in the output voltage, change in the output voltage, right? Pulse, this is a pulse width, indicates the pulse width. This is a one pulse we are having, right? And what is the width of that pulse? It is a delta. Width of the pulse is delta, right? So here from this, next V0 RMS for the modulated waveform, or VL RMS also we can say. Either you can say V0 RMS or VL RMS, right? V0 RMS or VL RMS, right? So it is, yes, come on, what is the RMS value? Whether it is a periodic signal, yes, what is the period? 0 to 2 pi, whatever the waveform we are having, the same will be from 2 pi to 4 pi, same will be from 4 pi to 6 pi, right? So it is 1 by 2 pi, right? Integration from, yes, 0 to pi, pi to 2 pi, right? So 0 to pi, again we are having the effective interval is pi by 2 minus delta by 2 to pi by 2 plus delta by 2, right? During this interval, what is the waveform magnitude? It is a EDC, so it will be EDC square into d omega t plus integration from 3 pi by 2 minus delta by 2. Again this is delta, so what about this? Indicates this is a delta by 2, and remaining one is also delta by 2. Okay, so we can write V0 RMS as, yes, it is integration from pi by 2 minus delta by 2 to pi by 2 plus delta by 2 EDC square into d omega t, right? Because the magnitude is output voltage is integration from 3 pi by 2 minus delta by 2 till 3 pi by 2 plus delta by 2. It is minus EDC, square of the minus EDC, it is again EDC square into d omega t to the power 1 by 2, 1 by 2. Are you getting the point, right? to the power 1 by 2. Next, this is to the power 1 by 2. Okay, next. So further simplifying it, we can write it as, can we take EDC square by 2 pi common, taking outside of the to the power 1 by 2, it is like EDC by root 2 pi, right? EDC by root 2 pi. Okay, into, this is after putting the limits, we will be getting delta plus delta, right? So it is like EDC under root delta, sorry, 2 delta by 2 pi. So it is like EDC under root delta by pi. Sorry, please be careful. This should be 2 delta, right? I'm sorry. This should be like 2 delta into 2 pi. 2 delta divided by 2 pi, right? V0 RMS is equal to EDC into under root 2 delta by 2 pi. So then after this 2 and this 2 will get cancelled. So what is V0 RMS? It is a EDC into under root delta by pi. EDC into under root delta by pi. Now this is the RMS value of modulated waveform, right? Modulated waveform. So by changing the value of delta, can we change the RMS value of the output voltage? Yes. Are you getting the point, right? So by changing delta, we can change the V0 RMS. Please make one correction. V0 RMS is EDC under root delta by pi, right? It's not like under root delta by 2 pi. It is under root delta by pi, right? Because delta plus delta, it should become a 2, right? So it is a 2 by 2 pi. So 2 will get cancelled. So it should be EDC under root delta by pi. Are you getting the point, right? So this is the method which can be used to remove or to control the output voltage, right? Next, can we derive the Fourier series analysis? Can we discuss the Fourier series analysis of this modulated waveform? And from this we can conclude that which harmonics are absent or which harmonic can move by the delta. Okay, so for modulated waveform, yes, what is the A0? That is average value. Yes, average value definitely it will be 0, right? Because from pi by 2 minus delta by 2 to pi by 2 plus delta by 2, it is a EDC. Similarly, 3 pi by 2 minus delta by 2 till 3 pi by 2 plus delta by 2, it is a minus EDC. So the average value will be 0. What is the AN? Whether the output voltage is a odd signal? Yes, it is a odd signal, because if we check the modulated waveform, yes, if we check the modulated waveform, if here it is a positive pulse, right? After 0, here we are having the positive pulse, right? So in the continuous waveform, it is 2 pi is like a 0 again, right? So whatever the negative pulse here, the same will appear here. Are you getting the point? So this pulse or this waveform is a odd signal. So as we know from the Fourier series analysis conclusion, for odd signal, AN value is 0, right? So AN value is AN is equal to 0. What is BN? We can write it is a 2 by T or 2 by 2 pi integration from pi by 2 minus delta pi by 2 plus delta by 2 EDC into sine of n omega t d omega t plus integration from 3 pi by 2 minus delta by 2 to 3 pi by 2 plus delta by 2 minus EDC into sine of n omega t into d omega t, right? So from this, after simplifying it, we can write it as Bn is equal to 0. Very important. Bn is equal to 0 for n is equal to 2468. If you simplify it, you will get the final expression. Bn is equal to 0 for n is equal to 2468 up to the infinity, right? And Bn is equal to 4 EDC by n pi into, very important, sine of n delta by 2 for n is equal to 1357 up to the infinity. The meaning is, yes, for the modulated waveform, A0 is already 0, AN is also already 0. So in the Fourier series expression, we are having like it is summation over n is equal to 1, 2, 3, 4, 5 up to the infinity Bn into sine of n omega t, right? Because AN and A0 are already 0. A0 by 2 and AN are already 0, right? So can we write? Are you getting the point? Okay. So it is like, so from this, can we say that again Bn is also 0 for n is equal to 2468 up to the infinity. Okay. So can we say that the modulated V load voltage waveform consists of only odd harmonics and it is having the expression, yes, VL is equal to, we can write it as final expression of Fourier series. Summation of n is equal to 135 up to the infinity 4 EDC by n pi into sine of n delta by 2 into sine of n omega t. Are you getting the point? It is like Bn, this term indicates it is a Bn into sine of n omega t. Again, what is a, again, whether the value of this Bn depends on the value of delta? Yes, okay, means suppose for the amplitude of the nth harmonic component is, it is 4 EDC by n pi into sine of n delta by 2, right? Sine of n delta by 2. Now, suppose if we are interested in removing a particular harmonic, so which delta we need to select, that we are going to discuss now, right? So suppose for the third harmonic, what is the VL3 magnitude? It is a 4 EDC by 3 pi into sine of n delta by 2, means instead of n here it should be 3, instead of n here it will be 3, right? Now if we select the value of delta by 2 such that sine of this 3 delta by 2 will become 0, sine of 3 delta by 2 will become 0, then can we say that the total output voltage due to the third harmonic will be 0? Yes. So when it will be, suppose sine of 3 delta by 2 to be 0, right? Then for that case, which delta we need to select? Because we know sine of pi is 0. Yes or no? Sine pi is 0. So sine pi 0 means 3 delta by 2 should be equal to pi, or it should be equal to 180 degree. So 3 delta by 2 should be equal to 180 degree. The delta should be equal to 2 into 180 by 3. Right, 2 into 180 by 3 means what? 120 degree. If we select delta is equal to 120 degree, then can we say that in the output voltage the third harmonic will be absent? Please check. If we keep here delta is equal to 120 degree, right? If delta is equal to 120 degree, replace this delta with 120 degree. So it is like sine of n into 120 divided by 2, right? So it is like sine of n into 120 by 2 means sine of n into 60. Yes or no, right? So which harmonic will be absent? Second harmonic is already absent, because for Bn even harmonics are, Bn value is 0 for even harmonics, right? So suppose n is equal to 3, so it is like sine of 3 into 60 degree, right? So sine of 3 into 60, that is the sine of 180. Sine 180 is 0, right? Suppose n is equal to 5, so it is a sine of 5 into, it is a sine of 300 degree. What is the sine of 300? Whether it is a 0? No. Means if delta is equal to 120 degree, only third harmonic will be absent from the output voltage. So if we are interested in removing the third harmonic from the modulated or the single pulse modulated waveform, then we need to keep delta value to be equal to 120 degree, right? Delta 120 means what? Delta 120 means we need to, yes, keep this delta to be 120 degree. This delta to be 120 degree means we need to turn on the switches S1, S2 at omega t is equal to, yes, 30 degree, right? And we need to turn off the switches S1, S2 at omega t is equal to 150 degree, right? Because it is 90 minus delta by 2 means this point, and 90 minus 90 plus delta by 2 means this point, right? Are you getting the point? So from this, if we keep delta is equal to 60 degree, the third harmonic can be removed. Similarly, if we want to remove the fifth harmonic, what delta we need to keep for removing the fifth harmonic? Fifth harmonic means what? 4 EDC by 5 pi. Here it should be n is equal to 5 and sine of 5 into delta by 2, right? So sine of 5 into delta by 2 should be equal to 0, right? So sine inverse of 0, it is a pi. Yes, so 5 delta by 2 should be equal, right? So 5 delta by 2 should be equal to 180 degree. So what is the delta? Delta is equal to 2 into 180 divided by 5, right? So it is a 360 by 5. 360 by pi means what? It is a 72 degree, right? If we keep delta is equal to 72 degree, if we keep delta is equal to 72 degree, then from the output voltage the fifth harmonic can be removed. Similarly, in general, for removing the nth harmonic, yes, the sine of n delta by 2 should be equal to 180 degree, right? So what is the delta? Sine of n delta by 2 should be equal to 0, right? So n delta by 2 should be equal to sine inverse of 0, that is what? Sine inverse of pi. Sine inverse of 0 means it is a pi. So n delta by 2 should be equal to pi or 180 degree. So n delta by 2 should be equal to 180 degree, right? So from this can we write delta should be equal to 2 into 180 divided by n, that is nothing but 360 by n. So for removing the nth harmonic, delta should be equal to 360 by n. Delta should be equal to 360 by n. You can cross check. For removing the third harmonic, yes, delta should be equal to 360 by n means what? 360 by 3. 360 by 3 means what? It is a 120 degree. For removing the fifth harmonic, delta should be equal to 360 by 5. 360 by 5 means what? 72 degree. For removing the seventh harmonic, yes, delta should be 360 by 7, right? And by selecting the particular delta, yes, we can remove the particular harmonic from the output voltage, right? If the harmonic is lesser, right? Now, yes, we are having the unmodulated waveform, we are having the modulated waveform, right? Now, what is the harmonic content difference between the two waveforms? In these harmonics, yes, 1, 3, 5, 7, right? All odd harmonics are present. But here, by selecting the particular by selecting the particular delta, that is a pulse width delta, we can remove one harmonic. Right? Means if we compare these two waveforms, in this waveform, yes, one harmonic is lesser than that of this, right? So can we say that this modulated waveform is more closer to the sinusoidal compared to the unmodulated waveform. Are you getting the point? Means single pulse modulation technique is used for voltage control as well as it is used for harmonic reduction also, right? Right? So this is about the voltage control by using the single pulse width modulation technique, right? Next, in my next video, we will be discussing about the multiple pulse width modulation technique for the voltage. Thank you. Thanks for watching.